So hello everyone, and welcome to this 18th webinar in the AO Africa R&D Facility webinar series. My name is Jeroen de Igrix. I'm a researcher at Vito Remote Sensing. We're a research institute located in Belgium, and we're a member of the AO Africa R&D Facility. For those who are not familiar yet, the AO Africa R&D Facility is a program funded by the European Space Agency. We're actively setting up African-European research collaborations, and we're offering various courses, such as this one, to promote the uptake of Earth observation across the African continent. In our webinar series, we typically invite various experts to talk about the latest developments related to Earth observation, both in terms of technology and applications. Before introducing today's topic and speaker, I would like to point out that we will have a presentation of about 45 minutes. During the presentation, we ask, of course, everyone to remain muted or to mute your microphones. You can ask questions through the dedicated Q&A button, which you will easily locate on the top of your screen. After the presentation, we will have a dedicated Q&A session in which we will try to answer the most recurring or upvoted questions. So please do not hesitate to use this Q&A button to ask all your questions during the presentation. So today's webinar is titled Mapping Our Planet in High Resolution, Advancing Land Cover and Degradation Monitoring Using Sentinel Data. This webinar will be presented by my Vito colleague Ruben van de Kerkhoven. Ruben is an expert in land cover and forest mapping based on satellite data and is also the lead scientist behind the famous WorldCover Global Land Cover product. So Ruben, please feel free to further introduce yourself. The floor is yours. Thank you.
Yeah, thank you, Jeroen, for this nice introduction, and also from my side, welcome everyone to this webinar. I'm indeed Ruben van de Kerkhoven, working at Vito Remote Sensing, and leading there a team working on land cover and forestry applications. So typically we map what's on the ground in terms of land cover, but also for forestry parameters from a local to a global scale. And it's my pleasure today to give you a bit more insights on the work we're doing related to land cover mapping at Vito. To kick off this webinar, I want to show you this image of a wildfire in northern Siberia. It's actually a RGB composite of Sentinel-2 data. The image already dates back from 2018, but it's still very relevant. Yeah, our Earth is changing every day. As you know, and yeah, land cover data, land cover monitoring really provides crucial information on how the Earth's surface is being used and how it's also changing over time. So this is an RGB composite. Actually, the nice thing of Earth observation data is that actually you can also explore the land cover in more detail by also looking to the different wavelengths of the spectrum. This is the same location, but here we actually are able more or less to look through the clouds, and you can also see hotspots of the fire. This is actually by we're looking here at the color composite, where we also have used the SWIR band, shortwave infrared band, as one of the bands for visualization, and this is this then shows these hotspots and also enables to look more or less through the clouds. So today, the main goal of today's webinar is really to provide you some more insights on the work we're doing at Vito related to land cover mapping, and more in particular, we will focus a bit on the power of Sentinel-1 and Sentinel-2 data for global land cover mapping. So first, I think most of you will be familiar with what Sentinel-1 and Sentinel-2 data, but if not, I will just give a short recap before we dive into several of the global land cover mapping initiatives that were carried out at Vito or are still being carried out. Finally, we'll also show you a use case of how this land cover data can be used for instance, monitoring land degradation at high resolution, and then we have some concluding remarks. So, as said, I think many of you are familiar what's actually the Copernicus program, but if not, this is a short recap that Copernicus is the European Union Earth Observation Program. It provides free and open data for a wide range of applications, and it also has several components, among which the space component. The space component contains a set of dedicated Earth observation satellites called the Sentinels. And today's focus will be on Sentinel-1 and Sentinel-2 data, with Sentinel-1 being a radar satellite and Sentinel-2 being an optical satellite. So here you see, if it works with the connection, a rotating globe of a Sentinel-1 composite and also a Sentinel-2 composite. As said, Sentinel-1 is a radar satellite. More in particular, it's a C-band radar constellation, because actually Sentinel-1, it's not one satellite but two satellites. Well, currently there are actually three satellites in orbit: Sentinel-1A, Sentinel-1B, and Sentinel-1C, which the last one, Sentinel-1C, was launched in December last year. Sentinel-1A was launched in 2014, Sentinel-1B 2 years later, but unfortunately Sentinel-1B experienced a critical anomaly at the end of 2021, which makes that it's no longer, let's say, capturing data. So Sentinel-1, as said, is a radar satellite, C-band radar more in particular. It has a revisit time of about 6 days, and with the two satellites. And it observes the Earth in different acquisition modes. For our land cover work, we are mainly using the interferometric wide swath mode, for which you can see a composite of several polarizations here on the left. Sentinel-2 is an optical satellite, as said. It's the Sentinel. It's also two satellites, and actually now it's three satellites, also similar as Sentinel-1. Sentinel-2A was launched in 2015, Sentinel-2B in 2017, and Sentinel-2C was also launched last year. So what's important of Sentinel-2 is that actually it has a really nice spatial resolution for several 10 to 20 meters depending on the band, and it also has 13 bands in total, and a revisit time of about 5 days at the equator. But the more north or the more south, closer to the poles you go, the higher the revisit time. So here you see, for instance, a false color composite of Sentinel-2 data. So false color composite means that actually we have here colored, we gave the near infrared band a reddish color, which makes that actually active vegetation is colored in red. This is, by the way, an image over the city of Antwerp in Belgium. So this is a false color composite from a single observation, and what you actually see here is a false color composite of over 1 year of NDVI data. So NDVI, the normalized difference vegetation index, it's a combination of the near infrared band and the red band. It typically, NDVI is a parameter which is related to the photosynthetic activity. So with Sentinel-2, we can get a time series of NDVI data. And what you can do then over 1 year, you can calculate temporal statistics, for instance, the 90th percentile or the 50th percentile or the 10th percentile. And this is actually what you see here in this image. Here we combine 3 of those percentiles. So in the reddish color, we have the 90th percentile. In green color, we have the 50th percentile, and in blue colors, the 10th percentiles. So what you see here actually is that the city center of Antwerp, so in the center of the image, it's colored bluish or black because it actually has a very low vegetation signal throughout the year. On the opposite, the whitish areas, or constantly vegetated areas, which are typically here the forests in the surrounding the city. And then what we have in the reddish or yellow tones are actually areas where we have we do have a peak in vegetation activity, but we also have throughout the year very low vegetation signal. And these are typically the agricultural fields, the croplands, which have experienced some harvesting event and also a bare soil period. So with this kind of temporal composites, you can really nicely see the different land cover types. And this is actually showing a bit the power of Sentinel-2. This is then a Sentinel-1 composite for different polarization modes, also of the city of Antwerp. And I think you can still see the different land cover here. We can denote the city center, which has high backscatter values because of the geometric properties, the material properties of the urban surface, and also multiple scattering effects. While the water bodies, so the river Scheldt surrounding the city, actually has a very low backscatter because it's absorbing the radar backscatter. And typically the forest areas and also the agriculture areas have some in-between backscatter signal. So what's nice about Sentinel-1 is actually that it's able to see also through the clouds. Sentinel-2 is an optical satellite, so which means that whenever there's a cloud, we don't have an observation. Sentinel-1 is an active satellite, and actually it's also possible to observe the Earth when there are cloudy periods. For those interested in getting hands-on with this data, you can consult these different data sets, Sentinel-1, Sentinel-2 data, on the Copernicus data space ecosystem, which provides access to these vast data collections, as well as some user-friendly tools for data exploration and processing. So what are now really the advantages of Sentinel-1 and Sentinel-2 for land cover compared to what we had in the past? First, there's the high spatial resolution. So we go now up to 10-20 meter of pixels, which is at global scale. It's free and open data, which is also really important. It has a very rich spectral information with these 13 bands of Sentinel-2. And also, like I said, it has the all-weather capability and sensitivity to surface structure thanks to Sentinel-1. And because we have also a very high frequent revisit time of both satellites, 5 to 6 days at the equator. It differs a bit when you deviate from the equator. We can now really go towards continuous monitoring, because these capacities of Sentinel-1 and Sentinel-2, they really lead to improved accuracy of land cover products. They enable also a more detailed and a more comprehensive classification, more classes, for instance. And finally, it also enables more towards a continuous monitoring, and near real-time change detection, which is really important. So this was to set the scene as an introduction for the reminder of the webinar. Now I will go a bit more in depth on the different projects, the different services that Vito has been involved of the last almost 10 years related to land cover mapping. First of all, I introduced already to you that the Copernicus program. The Copernicus program has a space component, as already introduced, the Sentinel satellites, but also the Copernicus contributing missions. But it also has a service component. Actually, Copernicus provides 6 services, which are listed here in this figure: the climate change service, the marine monitoring service, the atmosphere monitoring service, the land monitoring service, security service, and the emergency service. Vito has been mainly involved in the land monitoring service, producing, for instance, vegetation and biophysical products. However, part of this land monitoring service, Vito has also released this product, which some of you might know, which is the Copernicus Global Land Cover. It's a 100-meter global land cover collection. It was released in May 2019, and that it's, so like I said, it's 100-meter resolution, and it's a time series for the years 2015 until 2019. So it's annual products. It's at that time when it was released, the novelty was first of all in the resolution, because from the more traditional low resolution 300-meter products, this product made the jump towards 100-meter resolution. But secondly, another innovation was that besides a discrete land cover map, which you see here on this image with 23 classes, it also provided continuous cover fraction layers. So for every pixel, every 100-meter pixel, it provided the cover fraction of one of the 10 land cover classes. So what you see here, for instance, on this image, is an RGB composite of 3 such cover fraction layers, being the shrub cover fraction layer in reddish tones, the grass cover fraction layer in bluish tone, and the tree cover fraction layer in green tone. And this is actually very complementary information to the discrete land cover map, because with this continuous cover fraction layers, we can now really also per pixel assess what is really the cover fraction, and we don't just have a discrete label, but also really cover fractions for the different, let's say, land cover elements, land cover categories. The origin of this let's say, cover fraction layer, but also the discrete map, it's mainly related to the existing training data set that was used. Yeah, as part of this effort of a global data set was collected, global training data set by our partner ESA, about a bit less than 150,000 locations, each 100 by 100 meter. With 10 by 10 meter subsamples was interpreted. It was manually interpreted by our partner ESA. So in total, we have about 14 million 10-meter training points. So the innovation of this is that actually we have, on the one hand, a label at 100-meter resolution, but on the other hand, we also had the subpixels at 10-meter resolution, which could then be used for these continuous cover fraction estimates. I won't go too much in detail on the methodology which is behind the production of this map, but yeah, just in short, it used some data fusion techniques to because as an input, no Sentinel data was used, but ProbaV data. At that time, we didn't have the Sentinel data there, or there was just a very short collection available. So we used ProbaV data mainly as input, and then we had actually. On the one hand, both a classification step for the discrete product, but on the other hand, also a regression step for the continuous cover fraction layers. There were there was a lot of harmonization and consistency checks between the different products to ensure then a final high quality output product. The advantage of having this continuous layers as well as the discrete map really enabled that users could use both products to tailor, to create maps tailored to their needs. For instance, by combining several layers, you could create specific products for forest monitoring or biodiversity monitoring or crop monitoring. It was also used, for instance, this is the global forest management layer of 2015, which also used the same map as an input. So to further detail the different forest classes into different forest management types. So, like I said, what's really the innovation of this product? At the one hand, the spatial resolution at that time. Secondly, the continuous aspect, the cover fraction layers, and thirdly, also the quality. Yeah. What's important is that this product, there was a rigorous quality assessment by an independent validation team, and they estimated the overall accuracy of this product to be about 80%, which is still one of the best available global land cover products. If you're interested in the product, here you see a couple of links where you can obtain more information. So the product can be downloaded from the Copernicus Land Monitoring Service website. There's also a specific global land cover viewer. The data is also available on Google Earth Engine, also on Zenodo, and all details on how to use this product or on the algorithm can be consulted in either the product user manual, the ATBD, which is the algorithm description, and the validation report. So this was actually this land cover, 100-meter land cover for Copernicus Global Land was the first flagship product that we worked on over the past 10 years. It was then followed by this product, which also some of you might know, which is the European Space Agency WorldCover product for the year 2020. It's a 10-meter resolution based on Sentinel-1 and Sentinel-2 data. So we move from ProbaV to Sentinel-1 and Sentinel-2 data. And it also has a bit less classes now, 11 classes in total. So we go from 23 to 11. And that's mainly because in the 100-meter legend, we had different forest types, open forest, closed forest. At 10-meter resolution, we mapped tree cover, so we mapped the individual element, and we no longer these open and closed forest categories. This product it has become quite popular over the recent years, and also because of the quality and the popularity, also ESA requested the consortium also to generate an updated version. So there are actually two WorldCover products, one for 2020 and one for 2021. Difference between the two is that on the one hand there's a change in the reference year, but secondly also the WorldCover 2021 uses an improved algorithm, so-called version 2 of the algorithm. Let me just go back to the same area of interest, Antwerp. If we look to the 100-meter land cover from the Copernicus Global Land, you see that it depicts the urban areas here in red. It also captures the main water bodies here in blue color, so the River Scheldt and also the port of Antwerp, and also the different agricultural fields, agricultural areas in pink can be seen. More natural vegetation is colored in green, so different types of forest. This is then, however, for the same area, the WorldCover product, and you immediately see of course, the change in the resolution. Yeah, going from 100 meter to 10 meter, it's a dramatic change. At 10-meter resolution, it's now possible to see major roads. As you can see here, the ring road or the highways, also the runways are visible on the image. The water bodies are much better delineated. In the city, if I compare back to the previous image, in the city we can also now map the fine green elements, the parks, the trees, and also the boundaries, the borders of the croplands or the parcels are much better delineated at 10-meter resolution. This is another example of over a mangrove area, the Sini Saloum, a beautiful mangrove wetland area in Senegal. It's however endangered with cropland activities. And this is also one difference between the 100-meter map for Copernicus and the WorldCover project, is that actually mangroves were added as an additional class on request of the users. So in the 100-meter map, they are part of the either the open or the closed forest category. In WorldCover, there's a separate class for mangroves, as indeed there's a it's an important land cover class. This is then another area. It's San Francisco, downtown San Francisco in the US. You can see on the top the Golden Gate Bridge. So yeah, 10-meter resolution. It's now really possible to detect these fine elements. And also you see the Golden Gate Park, for instance, in the center, where we have the forest areas, but also some more grassland areas. The legend that was used in WorldCover, like I said, we go from 23 classes at 100 meter to 11 classes at 10-meter resolution. It's mainly based on the FAO, the Food and Agriculture Organization, land cover classification system. And it's relevant for a number of policies. Of course, I list here, this is a non-exhaustive list, but it's of course relevant for the climate and environmental policies, biodiversity and conservation conventions, and as well as for several sustainable development goals. However, what's important, and which is one of the what's feedback we often get from users, is that it's a pure land cover map or legend. We don't discriminate, for instance, between natural tree cover and a managed or a tree cover. Yeah, this is, for instance, oil palm plantation. In WorldCover, it's all mapped as tree cover. However, many users would like to see that there's a differentiation between, let's say, the managed tree cover, the plantations, and the natural tree cover. But this is not the case. Another limitation of the legend is on the, for instance, the grasslands, where we have both natural grasslands as pastures, all mapped as grasslands, and yeah, for instance, in Brazil, it's sometimes a remark we get that these should be it should be better to separate those classes. There are also, of course, other challenges with the legend. For instance, yeah, in the center you see cacao, which is we also map as tree cover, but typically this is these trees are somewhere between 3 to 5 meter. It's a very challenging area, and these kind of agroforestry areas would be maybe better to have them in a separate class. Also, vineyards, like what you see here on the right, we map them as shrubs in the legend, and yeah, I think this can also be considered as maybe a limitation for certain applications. What's also one of the limitations of let's say the two WorldCover maps is that actually they cannot be used for change detection. Yeah, because like I said, the 2021 WorldCover it contains both a different reference year, but on the other hand, it also contains an improved algorithm. And this is, for instance, visible in this image, which is on the top you see two composites, one for 2020 and one for 2021, of the Toshka lakes in Egypt. And what you see here, for instance, that yeah, in 2021 the lakes were much bigger compared to 2020. There was much more water in those lakes. And also in 2021, you see also the reddish circles, which are actually pivot irrigation areas, were also expanded. If we look here to the bottom, to the different maps, what you actually see is that, okay, the two WorldCover products, so on the left we have the 2020 product, on the right the 2021 product, it actually captures this change in water area. So this is really a land cover change that was nicely captured. But secondly, you see also that some of these cropland areas actually they moved from grassland to cropland. Yeah, in the left image, actually this is a classification error. These are not grassland areas, but these are cropland areas. While in the right image, it's correctly, so 2021, it's correctly classified. So I think this is an important message that the WorldCover products 2021 and 2020 shouldn't be used really for change detection, because it's in the methodology, there has been a change in methodology. So which makes that the product for 2021 captures both real land cover changes, but also changes due to this change in algorithm. Nevertheless, as said already, the product has become quite popular over the most recent years. Currently, there are more than 700 citations and counting. It's been accessed more than 5,000 times a month, for instance, on Google Earth Engine. It's open data, so it's a bit difficult to keep track of all the numbers, how many times it's used. But yeah, I think the number of citations, or for instance, the number of usage of on Google Earth Engine gives a nice indication that it's well picked up by the community. The quality of the product is also acknowledged by several scientific publications. This is, for instance, here a recent the results of this slide, for instance, shows here the results of a recent comparison activity of recent 10-meter global land cover maps. Because WorldCover is not the only 10-meter land cover map available. There's also the dynamic world dataset from Google. There's the ESRI map, ESRI Impact Observatory map, and there's also a product from China, and there are also other high-resolution products, like for instance the GLAD product from the US. However, this is Landsat-based, so 30-meter resolution and not 10-meter resolution. What we see really from this comparison exercise is that WorldCover, together also with the GLAD product, comes out as the best in class, and especially the fine spatial resolution, like what you see here on the bottom, it's really appreciated. You see here a comparison between a snippet for the same location over some highway junction between WorldCover, Dynamic World, ESRI, and GLAD, and you see that WorldCover and the GLAD product, they depict this the highways, while in the Dynamic World and ESRI product it's a bit more difficult to discriminate this. So why does WorldCover has this fine detail? Why does it have quite good accuracy? It's of course related also to the used training data. Actually, in the main component of the training data is the same training data that was used for the 100-meter land cover. As I said already, during the 100-meter land cover, interpretation was done at 10-meter subpixels. So we had a 100-meter grid with 10 by 10 meter subpixels. So we actually this training data could also then be used for training WorldCover. It was, however, further complemented with training data extracted from several ancillary data sources like OpenStreetMap for the built-up class, the Global Surface Water Explorer for the water class, the Global Mangrove Watch for the mangrove class, as well as some feedback points. So to produce WorldCover, actually, it's of course a lot of data. We split the world into a number of small processing blocks, which you see here on the top right. So you see here also the different UTM zones in which the Sentinel-2 data is delivered. So we split the world into processing blocks, about 1.4 million blocks in total. And for each of these blocks, we then first load the data. We clean the data. So we mask clouds, cloud shadows, and other artifacts. Next, we do compositing. So we to go from the raw time series to more irregular time series. And we calculate also different vegetation indices. And once we have these, let's say, cleaned and regular time series, we calculate temporal features. You have temporal statistics. I already mentioned at the beginning, for instance, this 90th percentile, 50th percentile, 10th percentile. So we calculate several of those statistics on the bands, on the indices, and these are actually our main features that were used in the subsequent classification task. Because once we had those features, we have the training data. Actually, what we did is we trained the classifier, a pixel-based classifier, CatBoost, which was at that time a really state-of-the-art classifier. What's important is, however, that we didn't train one classifier, but actually 3 models. One where we used Sentinel-2 data only, one where we used Sentinel-1 data only features, and one where we actually combined the feature stack from Sentinel-1 and Sentinel-2. So we had, let's say, in the three results. So when we run inference for these 3 models, we have 3 predictions, 3 sets of probabilities, and the results of these 3 models were then combined to create the final map. And in this process, also some expert rules were applied to correct for some general omission and commission errors. The whole workflow, of course, it's a lot of data, as I said already. It was run in a scalable and cloud agnostic workflow. WorldCover was run on Amazon, but actually could also be run on several of the datasets that were available at that time. The datasets which are now being replaced by the Copernicus data space ecosystem. So WorldCover, as I said, generated a lot of data. But while processing WorldCover, we also produced quite some side data, and for instance, we produced these percentiles, temporal statistics of the different bands. And this cloud-free, this is, for instance, can be used and create cloud-free composites of the world for the year 2020 or the 2021. And actually, as part of the WorldCover product site, we also released those side products. If you want to know more on for instance, this composite, which is a Sentinel-2 false color composite, please have a look to this to the blog, which you see here at the bottom. And actually, we did the same also for a Sentinel-1 composite. So this is all free and open data. So we have those available for the years 2020 and 2021. So you might download these and use for your application. Actually, these features and composites were already also used for several downstream applications. This is an example, for instance, of the Global Mangrove Watch. Some of you might know it. Previously, it was available at 30-meter resolution, but in the most recent update of the Global Mangrove Watch, so-called version 4, actually also Sentinel WorldCover features were used as an input to improve the spatial resolution of the product towards 10-meter resolution. So if you're interested in this product, please have a look also to the Zenodo publication, which you see here at the bottom. Okay, this is a bit what we have as existing products. Actually, many users now ask us, and actually almost every week we get some messages or emails from users. Hey, is there also a WorldCover for 2022 upcoming, or is there for 2023? Well, WorldCover stopped. It was actually a 2-year project, which got a 1-year extension to also produce the 2021 map. But in the meantime, WorldCover has stopped. So there won't be, let's say, a WorldCover 2022. However, what will be released, or what we can announce, is actually that more or less the same consortium from WorldCover was also awarded the Copernicus Global Land Cover and Tropical Forest Mapping and Monitoring Service. This is actually our ongoing effort, and what this service will do is actually it will continue the existing 100-meter land cover, which stopped in 2019. But secondly, it will also improve the spatial resolution towards 10-meter, integrating the lessons learned from the WorldCover project. And it will provide, as such, a dynamic global land cover service at 10-meter resolution for the years 2020 till 2026. So this service, so in the long name is Copernicus Global Land Cover Tropical Forest Mapping and Monitoring, quite a mouthful. So in short, it's LCFM. So from now on, I will call it LCFM. In LCFM, like I said, the first goal is to continue this 100-meter global land cover. So as I said, it stopped in 2019. LCFM will produce yearly updates for the years 2020 till 2026. Second goal is to enhance the existing service, so increasing the spatial resolution towards 10-meter, building upon the lessons learned from WorldCover. So on the one hand, improving the spatial resolution, but secondly, it will also improve the temporal resolution, because WorldCover, the 100-meter land cover, they use were annual products. Within LCFM, we will also move towards monthly products and eventually also near real time. It will look into further improving the quality of the products, and what's also important, it will really work on consistent change mapping. Like I said already, WorldCover, it lacked this consistency between 2 years. Within LCFM, we aim really to have consistent changes between subsequent years. Finally, there are also some specific products related to the tropical forest monitoring. So there's going to be a tree cover density product for the year 2020, as well as tree cover presence and change. Tree cover changes for the years 2021 till 2026. So it's finally extending the service on the one hand by this dedicated forestry products, but also by creating the sub-annual monthly products. So just in summary, so what LCFM will do, so LCFM, it's not a single product, it's a whole suite of products. It's going to create first land surface features and land surface categories at a monthly basis. So land surface features, so actually what are these? These are composites of the underlying Earth observation data, being Sentinel-1 and Sentinel-2. Cloud-free composites. These composites or these features will then be used for a first set of classification products at the monthly level, being the land surface categories. These are categories and probabilities of direct observable surface properties. Think about water, no water, snow, no snow, vegetated, non-vegetated. So these products, they will be released at monthly interval initially, and will then be used as an input to the annual products, being the land cover map at 10-meter resolution, so annual land cover, very similar to what we had in WorldCover, as well as a tree cover density product. This, however, this tree cover density will only be available over the pantropics, while all the other products will be available over the full globe. Finally, the 10-meter annual land cover will then also be aggregated to 100-meter resolution to create a 100-meter land cover map and to continue the existing service. Initially, the monthly products, or let's say the sub-annual products will be produced at monthly interval. Eventually, these products, like the land surface categories, the aim is also that they will become near real time, or let's say single scene mapping of land surface categories. So these were the land cover and forestry monitoring status products. LCFM will also generate change products. As I said, consistent change mapping is key within LCFM. So it will produce annual land cover change maps for the years 2021 till 2026, both at 10 meter and 100 meter resolution, as well as tree cover presence and change products also for the same period. Just to show you a bit what's meant with the pantropics. So this is actually the green areas. So what you see here on this image, for those areas we will produce TCD, so tree cover density, as well as tree cover presence changed, while all the other land cover products will be produced for the full globe. And of course, all this data will be free and open as to comply also with the Copernicus policy. What's also quite novel of this service is that besides the map products, also the training data sets will be released. Yeah, the land cover training data, the tree cover density training data, and also the tree cover presence change database will be released to public. So actually that users can also use it to train their own products or for their own applications. The training data has the way currently there's a new collection of training data ongoing. The approach is a bit different than that was used within WorldCover or the existing 100 meter land cover service. We use now an evolution of that methodology. Instead of, let's say, doing this pixel per pixel labeling, we're now labeling segments that were derived from the underlying Earth observation data, being Sentinel-2, and these are being manually interpreted. And as such, by using these segments, actually, also we can now, this training data set is actually deep learning ready, as it's called. It can be used to train also more complex deep learning methods, such as convolution neural networks, which are now, of course, very popular and offer a lot of opportunities compared to what we had 5 years ago. Finally, the aim of LCFM is that also we're going to release the code base and how the different products were made. So LCFM will be produced using the OpenEO platform. For those not familiar with what OpenEO is a bit similar to Google Earth Engine. It's like the European alternative, but fully open and transparent. And actually, by on the one hand releasing the datasets, the training datasets, as well as the code base, the idea of LCFM is actually we would create a dynamic land cover service that users could further tailor the output products or use these outputs to create their own land cover products besides the default product that will be generated. So LCFM, it's a 4-year service contract. It started about 1 year ago. We concluded more or less the ramp-up phase. We're now starting the global production of our first production year, being the year 2020, and the aim of this is really to publicly release those 2020 products before summer. Then we're going to work on the change products for the year 2021, which the target release date is about one year from now, and then actually the production speed of the service will increase, and every 3 months, more or less, a new year will be added to the data set. So a lot of data is coming. If you're interested in this service, in these products, I would advise you to keep an eye on the Copernicus Land Monitoring Service website or also the social media channels. Okay, this was more or less on the different, let's say, global land cover activities that we are involved. Now I just want to zoom in on one of the applications of those data sets, being the monitoring of land degradation at high spatial resolution, which actually was something we developed together with our partners as part of the European Space Agency Sentinel for Land Degradation Neutrality project. For those that are not really familiar with land degradation and land degradation neutrality, well, there is an SDG indicator, so a Sustainable Development Goal indicator called 15.3.1, which actually obliges countries to report the proportion of land that is degraded over their total land area. And this is based on 3 sub-indicators: trends in land cover, trends in land productivity, and also trends in carbon stock. However, traditionally, the monitoring of these this SDG indicator is based on low to moderate resolution datasets. For instance, like the ESA CCI land cover, or the C3S land cover is being used mainly to assess the trends in land cover. Of course, yeah, this is 300-meter resolution. With the Sentinel's data, Sentinel 1 and 2 data now available, actually it's also possible now also to go to increase the spatial resolution of this land degradation assessments. And this was actually the main goal of the Sentinel for Land Degradation Neutrality project, was to advance the methods and explore how we could improve, let's say, the spatial resolution of the monitoring of these different sub-indicator for SDG indicator 15.3.1. What we have been establishing within Sen4LDN was actually an automated global land cover change algorithm. Yeah, as I said, one of the downsides of WorldCover was that actually it was not able to capture land cover changes. Within Sen4LDN, actually, we developed such a consistent land cover change algorithm which works at the global scale. Actually, it's a similar approach will now be implemented within the LCFM service. So this algorithm is able to generate annual consistent land cover maps, both discrete products but also more continuous products. And actually, this can then be used to assess land degradation in a more continuous way. For those familiar with the SDG 15.3.1 reporting, traditionally it uses the so-called one out all out methodology, which says that if one of the sub-indicators, let's say, indicates a degradation, the overall indicator also is recorded as degraded. Within Sen4LDN, actually, we explored the possibility to go beyond this discrete mapping and also as creating a more continuous monitoring. So if you're interested, want to read more on those results, I advise you to have a look to the website of the project, esa-sen4ldn.org, where you find the different outputs. We actually have created prototype datasets, annual land cover, as well as annual high resolution productivity for several countries, being Uganda, Colombia, as well as Portugal. So all the data can be consulted from that website. So yeah, I'm more or less at the end of my talk. I just want to conclude with some final notes. Based on all the things you've seen now, I think we can say that really, yeah, land cover monitoring, it's really of paramount importance. It enables informed decision making. And yeah, we are living really in historic times. Our planet is changing, So it's really important to have timely information on the status and the changes of our planet. Over the past decade, I think what I showed you in this presentation is really more or less an overview of a bit less than 10 years of work. We've seen really a shift from a more moderate resolution monitoring and static maps using more or less basic machine learning techniques to higher spatial resolution maps. Yeah, so we went from 300 meters first to 100 meters and now to 10 meters, and actually also already the first sub 10 meter products or global products are already starting to appear. We also went to from annual maps, or let's say first epoch maps, then annual maps. Now we're moving towards monthly and eventually also near real-time monitoring. And also the legends, they become more and more detailed. Yeah, we see richer training data allows also for more sophisticated machine learning algorithms. The whole deep learning evolution enabled also to include contextual features in the classification process, which makes it also possible now to map classes really which have a contextual fingerprint. And what we also saw is that we move more and more towards customizable maps, customizable solutions, allowing tailored solutions for diverse applications. There is no one fit all map. Yeah, every application needs its own specific legend, specific resolution. And what we see now is that really we have now the data, the infrastructure. It's all becoming available to have this on, let's say, dynamic land cover services. So we went over the last 10 years from, let's say, land cover mapping to more land cover monitoring and characterization, to a transition towards more dynamic and insightful analysis. And like I said, these are really, at least from a mapping perspective, quite exciting times. Yeah? There are endless, almost endless possibilities. Almost everyone can now make a map. Yeah. However, creating a good map remains a challenge. It's not because you can do it that it's a good map. And what still remains the holy grail for all the mapping activities is really this accurate change detection. Yeah, it's essential for decision making. And what we see now is really over the last years, a lot of progress is being made in this consistent change mapping. And with the LCFM service, we hope to also bring there the next step with a consistent annual change product at 10 meter resolution. So with this, I want to conclude my talk here. It's a bit longer than originally foreseen, but I think that's fine. And I think we open now the floor for any questions.
Thank you, Ruben, for this very nice presentation, for this nice overview of all recent global land cover activities, and how this indeed involves towards land cover monitoring and change detection. I again want to point out that if people have questions, they can still use the Q&A section of this Teams meeting to put their questions there. We have had some questions during the presentations, maybe a very brief one to start with, Ruben. There is one question about the spatial resolution of the Sen4LDN project. Am I correct that this is consistently at 10 meter?
Yes, indeed. In Sen4LDN, we're mapping land cover changes, trends and land productivity at 10 meter resolution. So for the land cover, we're using an evolution of the WorldCover algorithm. For the land productivity, actually, we use a rather similar approach as that is used in the European Phenology and Productivity Service. So it's based on TimeSet, and it's actually the colleagues from Lund University, Lars Eklund and its team, that were responsible for this algorithm.
All right, thanks. Meanwhile, while maybe other questions will pop up, I want to stress again that all the products that Ruben has been shown, they are freely accessible to everyone. So I have put some of the links where you can find more information about these products in the Q&A as well. I also want to point out that this presentation has been recorded, obviously, and will be published later on. So you will be notified and will be able to rewatch this full presentation. Ruben, there was one question on, at the very beginning of your presentation, you showed these percentile images, how they actually were computed, because they seem to be a very nice concept to visualize land cover.
Yeah, indeed, these percentiles actually they more or less capture the annual dynamics in one image. Yeah. So the percentiles, typically what we do, Sentinel-2 but also Sentinel-1, it has a temporal resolution 5-6 days on average. At least at the equator, a bit higher when you go up closer to the poles, as I already mentioned. So we first mask for Sentinel-2, we mask all the clouds. We create composites. Every 10 days we create a composite over the median composite over the 10-day period. So we have then cleaned composites. For instance, if we would have a vegetation index like NDVI, if let's say you go from the dry season or the winter season where there's almost no vegetation activity to the summer where there is or let's say the leaf on season when there's a high vegetation activity, you typically would see this rise in your temporal profile. Depending on the number of seasons over a year, you would get, for instance, a Gaussian curve. And what we do then is actually on this full profile, we calculate the temporal statistics over this year. So what is like from the annual profile, the 90th percentile, what's like the median, and what's like the 10th percentile. So the minimum, the median, and the max. So that we use 10th and 90th percentile instead of min and max. Why? Because there might be still some noise in the from residual clouds, residual shadows in the time series, and taking the 10th or 90th percentile increases the robustness of this. So typically this 90th, 50th, and 10th percentile are used, and these are actually our main features that we use then in our subsequent classification, because indeed, like I said, it gives per pixel. It captures the temporal dynamics into a single value or per pixel. Yeah.
All right, thanks for that clarification. We have one more question on the amount of training data that is typically used whenever you're doing things like land cover mapping. Can you comment on that? The question specifically is how much training samples would you need to do an accurate land cover map of a certain watershed, for instance? Is there any idea there?
Yeah, of course, this depends a bit on the model, the methods you're using. Yeah, like I said, I showed in my presentation that in the beginning we went from, let's say, more simple machine learning. In the 100-meter land cover, for instance, we used random forest. In WorldCover, we used CatBoost, and now in LCFM we're going to use the more elaborate deep learning algorithm. Within the WorldCover and also the Copernicus Global Land 100-meter land cover, we used the same set of about 150,000 training data locations. For the 100-meter algorithm, we used 150,000. So one value per 100-meter let's say location. In WorldCover we also subsampled and the individual cells, so we had many more training points, and this has seemed sufficient for our let's say global map products using either CatBoost or using random forest. Now what we see is that now in for instance LCFM, we're going to use a deep learning approach, and therefore we need more training data. So we have been extending the size of our patches, almost 10 times as large as we had them in WorldCover or the 100-meter mapping. So because you need on the one hand you need to have a larger spatial context also to learn the spatial features which are of relevance for your classification, but also in order to make to train the algorithm, these deep learning algorithms, you need just also more training data. That said, we see now also more and more an evolution towards things like foundation models, which would need less training data because you use already some pre-trained input in your model. So it's difficult to give one number of how many training data you need because it really depends on the type of modeling approach. So we have 150,000 samples across the globe for a pixel-based algorithm should be okay. For deep learning algorithms, you might need larger areas to learn the spatial context.
Thanks, Ruben. And maybe to complement on that, it might not only depend on the specific modeling approach you're using, but also the landscape complexity in your local use case or the local area that you're looking at. And this relates to a question that we got, like how do you deal with very heterogeneous landscapes? Do they typically require much more training data? And do you also see maybe that the accuracy of the global land cover products that you've been mentioning is clearly affected or different in those areas?
Yeah, thanks for the question. That's a very good and valid question. Typically, what we see in our maps is that the heterogeneous landscapes, being several areas in, for instance, in Africa, so the Mayombe woodlands or the Sahel region, these are complex landscapes. Yeah, it's difficult to map them. And we typically have lower accuracies in those regions. Yeah, so the more heterogeneous, it doesn't really. I would say that it depends a bit also on the landscape, because what we see, for instance, in certain more areas like in Europe or in Asia, we do have high overall accuracies, although also the landscape is also heterogeneous. However, it's more a bit regular. It's a bit easier for the classifier to learn the patterns and the landscape, and also it's more easy to interpret the training data. Typically, what we're having in high heterogeneous regions like I said, Mayombe woodlands or savanna landscapes, there the training data is also a bit of lesser quality. So typically more heterogeneous landscape, it decreases the quality. Of course, in the Sahara Desert, the quality of the product is usually good. So it's it's a bit a combination, let's say, of the heterogeneity, but also the complexity of the structure of the landscape. Yeah, a well-structured, organized landscape is easier to characterize because you have better training data. You have clearer spatial features in your classification than let's say a more heterogeneous area.
Thanks, Ruben. Melsu, I see you still have your hand raised, but I hope we answered your question there. Let me know in the Q&A if you still want to. Okay. So please feel free to ask more questions for Ruben in the chat. Maybe while we wait, a question related to that. Ruben, do you think that given these heterogeneous landscapes, we need to evolve towards even higher resolution land cover mapping? So should we go really beyond the 10 meters? Are there any plans for that in the future?
Of course, the higher your spatial resolution, the better you can characterize and map the individual elements. That said, it's also mapping the individual elements also comes with a challenge, because at 100 meter resolution, for instance, a heterogeneous let's say area over in the, for instance, the Sahel region, we would all map it as open forest. It's this is so it's rather easy. You just map it open forest. At 10 meter resolution or even beyond, you want to map the single landscape elements. Is it a shrub? Is it a tree? Is it grass? And that it gets much more complex. What we saw, for instance, in our land cover projects, for instance, that in Australia, we do have regional statistics on the accuracies. And Australia had the highest overall accuracy per continent in the 100 meter map, but it had the lowest in WorldCover. And that's because the whole inner Australia is actually a mix of bare, grass, shrubs. It's a xeric shrubland, so it's extremely hard to map it. So I think what we want to go is also at 10 meter resolution. We should also go towards more continuous mapping. Ideally, we also have fraction mappings at 10 meter resolution. It's something we're exploring. But I see also now that with the availability of planet data, for instance, we see now also the emergence of higher resolution products. I also know that some of the upcoming there are some ongoing discussions on, let's say, also increasing the spatial resolution of the next generation of Sentinel-2 towards 5 meter resolution. So there's going to be more and more higher resolution available, and it will enable potentially a better mapping of the landscape, but it comes also with challenges. There's more data. You need also to have the training data at that resolution. It's also important that the geometric accuracy of our training data that you're using is excellent. Otherwise, because you start to having some geometric shifts, and then it's the model performance is a bit more poor. So
Thanks, Ruben. Meanwhile, other questions keep coming in. So we have a question on the tools that you typically use. So just to be clear, Melsu, regarding your question, we always used a supervised classification approach, but you're wondering whether you should be using Google Earth Engine rather than a GIS application. I would say, to shortly answer that, obviously cloud-based infrastructure like Google Earth Engine, but especially now also the Copernicus data space ecosystem. So Europeans' answer to Google Earth Engine, let's say, allows way better to scale up your applications. For instance, for global land cover mapping, as Ruben presented, this is way easier to produce an actual global map using these cloud-based platforms. Another question that we have, I was wondering if you could kindly provide some insights on how species such as eucalyptus trees can be mapped. So we have talked about generic land cover classes, but what about individual tree species?
This is of course a challenge to go really to species level. It requires training data. I think what we can do, I think, or what we're looking in is to for instance, go beyond a tree, but also mapping the phenology. If it's a deciduous tree, if it's coniferous tree, that's something we can do at a global scale. What going really to single species, that really requires local training data. It's something we don't really plan. I think what the vision we have there a bit is like that with all the training data, all the data products, the features that will be generated. For instance, part of this LCFM is that a user could use the workflows, upload his own training data, then to create, for instance, the map of the local species of eucalyptus. It all boils down to training data, availability. This is for any, let's say, type mapping, being it tree type, being it crop type. Gathering this training data it's extremely important, but it's also a very hard task to do. So having the right reference data would enable this. But it's not there yet at a global scale.
Thanks, Ruben. This maybe also brings me to the topic about land use versus land cover. You've already mentioned it during the limitations of the WorldCover product, that it's really mapping land cover and not land use, especially now in the context of the new European EUDR policy. Land use mapping is becoming really crucial, like knowing where tree plantations are, knowing when natural forest was converted into plantations. Could you share any plans related to that aspect, maybe?
Yeah, thanks. Yeah, that's also a very relevant question, of course. Land use. What actually makes that a plantation differs from a natural forest? Yeah, there might be a change in spectral signature for some species. That's possible, but often you see also that they have a different context. Yeah, you can, if you look to, for instance, palm oil plantation from on a satellite image, compare it with natural forest. You can see it, that it's based on the patterns, based on the structure, that it's palm oil. With what we see now is that with the let's say the emergence of the deep learning techniques, which take into account the spatial context, it's becoming now more and more possible to map land use, because typically land use has a spatial component to it. It's also, we have in WorldCover, we have agriculture, we have cropland as a class, which is typically which is actually more a land use class than a land cover class. But the agriculture, we also we can differentiate it even better now that we can use the spatial context, being the fields as an input. So what we see is that actually with the whole emergence of deep learning techniques, we see that we can now start getting beyond traditional land cover. However, it's not for all classes. For some classes we can map. So we're for instance looking into mapping different forest management types. We're having also another ESA project called World Agro Commodities, in which we together with our partners try to map the different commodities, also considering the UDR. So I think it's an ongoing effort. I see some products appearing in the next years more and more towards land use mapping, and that will be mainly because of the deep learning techniques that are now available, that become more performant every day, and also the training data sets that are being gathered. That said, like I said, it won't be possible for all land use types, but at least not in an automated way. But for some types, it will become possible.
Thanks, Ruben. And maybe one last question to wrap up this session. Also related to looking ahead into the future, there was a question from the audience about what about projections of land use, cover in the future. I guess this requires a totally different approach, like more a land use modeling approach. But yeah, maybe any relevant activities that you can point to there.
Yeah, well, this is indeed a bit beyond scope of what we're doing, what we're trying to do in the projects at yeah, like LCFM, like WorldCover, like the 100-meter land cover. It's more mapping the status and the changes. It's mapping the actual observations. But indeed, the mapping the future is a total different science almost. I know for instance, at FITO, we have also some colleagues that are working on land use mapping projections and models. And with having now access to this global, let's say, status datasets for a certain year, they're now able to better calibrate their models, or let's say the initial states of their models. So it can be used mainly for calibration of those land use models. Yeah. That's my answer. Personally, I don't really have the experience to answer that, but I know, yeah, that with better reference data, better status maps, you should be able normally also to get better future projections also.
All right, thanks a lot, Ruben, for your detailed answers to all of our questions. I want to highlight that if you would like to learn more about these deep learning techniques for land cover or even species classification tasks, I'm sure they will be covered in much more detail in some of the upcoming EU Africa courses, both online and face-to-face, that we still will be organizing. So please keep an eye on our R&D website for any future opportunities. And then I would like to thank, obviously, all of the participants for their attention and their engagement. And I wish you a very nice day. Thank you so much, Ruben.
Thank you. Bye.